probably the hardest slide of all, namely dynamic programming. And so we went through a fair amount of detail. Okay. What we did is we basically looked at how you can transform graphs into then triangulated graphs and then build junction trees out of that. And then, well, how to do message passing. And that was probably a little bit rough. Don't worry, you won't be needing that type of set of tools for the rest of the lecture. But I want to give you a little bit of an overview of what can be done once you actually need to do interactive, inference in large and more interesting graphs. And I'm not assuming that if you've never seen this before that you will just get it right away. So don't feel bad if this was tough. Okay. Now, we're going to do something very simple. First, we'll do clustering, right? So here's the basic idea. So before that, we had the model where we had a very simple graphical model before, right? Okay, before that, what we had is we have basically those instances xi, and they are observed, and then there's some parameter, maybe theta, and we basically observe those guys, right? That's basically what density estimation would do. It would like to, well, infer this parameter theta, which models all the data. Now what we're assuming is that this density model is a little bit more sophisticated, so we just make the box bigger. We make it bigger by putting some y's in it. So we have the xi's. Fortunately, I'm not very good at drawing solid circles that are readable. And I have some yi's coming here. They are unobserved. And then they are drawn from some phi. Okay. So once I do this, this is basically clustering. What I'm saying is, I pick some, cluster, and then for that cluster I draw, from whatever associated distribution. One of the reasons why I might want to do that is because I might actually care about having a meaningful model for, partitioning the data into subgroups. That's one of the reasons why I might do that. Another reason why I might do that is because I might have a fairly simple model that for something that might generate my data, like a Gaussian. But I realize that in practice, well, Gaussians are maybe not going to get me that far because they're unimodal and very nice and have lots of symmetry properties, and a lot of real data isn't of that form. So if I have data that is multimodal, then maybe a mixture of Gaussians is going to be a better approximation. So the two main reasons why I might want to go from this to that is just that I could actually characterize more interesting distributions with it, or I might endow those unobserved variables with some meaning. And mind you, I did not claim that this meaning that you're going to extract from that is in any way meaningful in the sense that it actually corresponds to reality, but it might be meaningful enough that a human can do something with it and that they can reason about it. Mind you, being able to reason about it doesn't mean that it's actually the truth. Simple example. I can have a very bizarre model about why the sun rises, like I could imagine that there's somebody on a chariot dragging the sun over the sky, and still make fairly accurate predictions of when there's going to be noon and evening and why it's going to be day the next morning. The model is horribly wrong, but still I can actually reason fairly accurately with it. And in a lot of graphical models, you may get the model horribly wrong, but you'll still be able to reason accurately with it. And that's the level at which I think it's sufficient to extract meaning from data. So I'm not trying to discover the true fundamental causes. And this is where sometimes graphical models actually become really dangerous, right? So if you use them in bioinformatics, and then you use your model, you discover some structure, then you say, oh, yes, and this is exactly now the biology underlying it. This is a very dangerous step. For that, you need to do actually a lot of additional experiments to verify it. Might be a good tool for finding hypotheses to verify, but you can't use such a setup as what I'm describing now, basically structured sets of random variables, as evidence that certain things are true. For that, you need to do more work. Okay. Now, does anybody have an idea how I can actually transform this model into that? How can I go from the left to the right? Okay, anybody has a suggestion how I can do that? Okay, it's very easy. I just need to integrate out the possible values here for all the y's. If I integrate it out and integrate this guy out, I get exactly that model back again. To drive home the point a little bit more, let's actually write out the math. So if I have p of x and y, and I'm just going to call those two variables the same thing, doesn't really matter, parameterized by some theta, right? Well, this is just given by the product, I going from 1 to n, p of xi given yi and theta times p of yi given theta. Right? So in that case, and of course, this will now depend on, however I pick theta. So from that, it follows that p of x, parameterized by theta, is just given by the sum over all possible values y of p of x and y given theta, which equals, in this case, and factorizes actually fairly nicely, I going from 1 to n, p sum over all the yi's in my set y, p of xi given yi and theta times p of yi given theta. And I now just get this new variable, p of xi given theta. So I can see how this model can be transformed into that. What has changed is that here we had fairly simple constituents. For instance, we had Gaussians and the multinomial. Whereas now in that case, we just have multimodal distributions with up to maybe 500 modes, okay, which is a much nastier object to deal with. And so in some cases, performing inference in this model is hard, whereas performing inference in this model is going to be a lot easier. I'm going to show you exactly a few means how you can perform inference in this setting. And what this will do is it won't only show you a reasonably useful, namely mixture of whatever graphical model, but it'll also teach you a little bit various inference techniques that you can then apply. Okay. So let's try that. So here's the basic idea of the graphical model. And all I've done just on the right-hand side is now I've just added the dependency on alpha and beta, which are now hyperpriors and hyperparameters. Okay. So this is just writing things out in equations. Now, a few things that we could cluster. Right. So emails, news, text, queries, URLs, products, users, locations, events, ads, spammers, abuse. So for instance, with spammers, I might want to cluster them because maybe there are only 20, 30 different pieces of software out there that generate spam, and you might actually want to find out which version they're using. That's not uncommon. Sometimes people use combinations of that. Sometimes they use various address lists and they just merge them, and then they decide to send emails around. So if you want to know the going rates for stuff like that, there's a website that you can visit. It's called Freelancer. Graphical.com. So there people post requests for, well, services of all kinds. For instance, you can post a request for designing a web page, building a web server, or also requests like, I need 100 links from web pages that have a page rank of at least 4 to my web page, or I need within the next 2 weeks 100,000 Facebook likes, or I need maybe 10,000 email accounts of some provider. And if you look at it, then people bid for it, and so it's actually an amazingly exciting view of what you can see what's happening in the sort of not quite so legal part of the internet.
What did you see?
Fun? So, well, what you can find is, for instance, that at the moment the going rate per account is in the order of a cent. And if you have a Facebook verified account, it goes up to $1 or so. So it's actually really quite informative, because you can use it a little bit as feedback as to how well your spam filtering algorithms work. You might want to cluster ads. Why would you do that? Suppose I have a Pepsi ad and a Coke ad. Then knowing that those two ads are probably very similar in their target demographic will help me a lot to determine where to display and how to price the Pepsi ad if I've just been running the Coke ad before. Well, news, of course, if I cluster them, it's probably useful if we have all the news about philandering politicians together, except that sometimes you then get interesting things like when you, for instance, look at the Anthony Weiner case, all of a sudden you get the story of Schwarzenegger mixed in. There's a reason for that. You might want to cluster products, and maybe sometimes a flag clustering isn't a very good idea. Maybe you actually want to have an entire ontology. So there are a lot of cases where clustering is actually a good way of structuring data. I'll afterwards show you a few cases where clustering is actually a pretty bad idea. And as a rule of thumb, any structure that you're going to impose and try to infer, if you have a meeting with engineers in your room, and they argue about which partitionings are right, it probably means you haven't got the structure right. OK, so how do we do that? So one way is we draw a cluster label from a discrete distribution, and maybe then we draw x from a Gaussian for a given cluster. So that's exactly this model here, right? It's a Gaussian, that's a multinomial, and then up here we just use a Dirichlet as a conjugate prior for those latent variables. Maybe here we use as a conjugate a Gauss-Wishart. So in the previous lecture, Manfred had some things like traces of matrices and determinants of them. And actually, if you look at the Gauss-Wishart distribution, you get exactly those objects out of it. So it's not so much of a coincidence that those things show up in a few places. Trouble is, of course, we don't really know those cluster variables. But of course, if we knew the parameters well, then we could get y fairly easily, right? Because then you can, for instance, do a maximum likelihood. Because if I observe all the guys here, then for these, they're all nicely decomposed, and I can just do a maximum likelihood estimate, or I can just integrate out over that. On the other hand, if we knew this y really well, then we could get all the other parameters easily. For instance, if I knew which points belong to a cluster, then estimating the mean and covariance for a normal distribution, if I tell you all those points are drawn from a Gaussian, is kind of trivial. So it's the chicken and the egg problem, right? If you knew the clusters, you could actually, well, get the parameters, get the cluster assignments. If you knew the cluster assignments, you would know the clusters really well. So how can we bootstrap this? And there are a couple of ways how we can do this. So the simplest, and I sort of alluded to that already in the lecture before, is k-means. And it's kind of a caricature of what a graphical model does, namely as follows. You fix a uniform variance for all the Gaussians. You fix a uniform distribution over all the clusters, so each cluster has equal weight of occurring. You randomly initialize everything. So these are horrible assumptions, right? And then you just find the most likely cluster for all the data points, and then you find the most likely center for a given cluster. And you just repeat until you get stuck in some local minimum. It's very simple. And you can easily implement it in MapReduce. But it's not very good because it doesn't give you a particularly good probabilistic representation. You can get stuck in local minima and so on. So here's a simple example. You take some data points, you start with them, you partition, and then you update, and you keep on doing this. So it's very simple. Here's a better way, EM. The expectation maximization is actually nothing else but a variational approach to solve a problem. So let's just write out that problem. So the optimization problem is I want to maximize with respect to the cluster probabilities, the means, and the variances, the overall data likelihood. And so I can just write it out, right? And unfortunately, this is really nasty to solve. So one thing I could do is I could just run BFGS or some other non-convex solver on that. And people have done that and actually showed that it does some fairly decent things. So for instance, people have done that with topic models. And under certain parameter settings, this gives you an amazingly fast algorithm. But in general, we have a problem of that form. And for this, you use what's called a concave convex procedure. I'm just going to show it to you a little bit better than what I can do on a slide. So basically, say you have some function which looks like so. Okay. Then maybe you can decompose it into this function here. And another function that looks like so. Okay. Now, if I wanted to minimize this, and so the black and the red function are both convex. Can you? Yeah, you can actually see the colors. That's good. Okay. So the black function is concave, the red function is convex. Yeah, obviously. So what I can do now is I could, for instance, go and just minimize the red function, which is convex, and I can find easily a minimum. Okay, so let's start with doing that. Okay, it's kind of awkward here because it already has the minimum. So let's start at some suboptimal point here. Okay, let's say here. Now, at that point, I can get an upper bound on the concave function. And I know because it's a concave function that I can get an upper bound by just taking a tangent. Right? Now, I basically minimize that black tangent plus the red function. Okay, so I end up maybe here. So shifting everything a little bit to the right. So now at this new location, I recompute my upper bound. It's going to be tighter. It's tighter because, well, it was an upper bound before. At the new location, I compute another tangent. It's tighter now. I minimize that upper bound again. And I get maybe here. And as you can see, you're basically done. Compute another tangent. And maybe then we find the global minimum here. So what I've done is I've basically preserved the convex part, and I kept on upper bounding the concave part by tangents. Now one can show, so this is a paper that Vishy Vishwanathan, Thomas Hoffman, and I wrote a couple of years ago, and there's also another paper by Alan Yule and Rangarathan, which, so they called it a concave convex procedure. It's also called DC programming, as in difference of convex function programming. It's called the EM algorithm. It's also called the M method. So these are the four names I know for the same simple idea, namely what I've just shown you. And each of them have pretty much spawned a research subject of their own. So you can see how you can make out of this probably 10 to 20 tenured professors, right? So it's not too late. Maybe you give it a new name and you get tenure for it in some new field. But joking aside, this very simple procedure is exactly what we're going to use now for non-convex minimization. Here's how it works.
Maybe you want to mention that every function can be decomposed potentially.
Of course. So every function that I have, all I do is, for instance, I could just go and take the second derivative, and whenever it's positive, I throw it on one function. Whenever it's negative, I throw it on the other function, integrate by parts up, and I'm back home. So any function can be decomposed. The interesting thing is that I can use exactly that idea of having an upper bound that's tightened up at step by step to get an upper bound for EM. And this is, to my knowledge, the shortest derivation for EM for variational inference in general that I know of. So suppose we want to maximize log p of x parameterized by theta. Okay? Now, since I want to maximize that, if I maximize the lower bound of it, I'm at least guaranteed to make things better if my lower bound was tight at the point where I started the optimization. Now, log p of x parameterized by theta is greater or equal than log p of x parameterized by theta minus the KL divergence between some arbitrary other function q of y and p of y given x and theta. That holds regardless because the Kullback-Leiber divergence is never negative. And I'm not going to prove that. I would imagine that Manfred might have proven that in his slides. And obviously, whenever q of y equals p of y given x, then, well, left and right hand side have the same argument, so the KL divergence is 0. So for those arguments, the inequality is tight. And I also know that it's if and only if. OK, good. So now I can just write out the KL divergence. This is just one big fat integral with respect to q, right, this guy here, of, well, p of y given x minus q of y. Furthermore, what I'm doing here is I'm just pulling in log p of x given theta. Well, I can pull that in because it doesn't actually depend on y, and the integral here is 1. So it doesn't change. But now something amazing happens. The amazing thing that happens is that, well, p of x times p of y given x is just p of x and y. Right? It's just conditioning. And now what I get here is it's the expected log likelihood of the data and the latent variables with respect to some reference distribution q of y. And then here in the back, I just have an entropic term. So what that means is I can just go and pick some q. I now maximize this expression here with respect to theta, because that one doesn't really depend on theta. I then recompute q, and I keep on iterating between those two things. And that's EM. Now, if it just should so happen that I don't really have, that I'm not able to really get this p of y given x expressed explicitly because the function doesn't look particularly nice, then this is called variational EM. Again, people have gotten tenure for things like that, where all they did is they just said, well, you know, rather than a general function, we now pick a structured class of functions and we solve for that. That's structured EM. And for instance, variational inference in Bayesian models, well, so there's this very long and nice book of Chris Bishop, which has a lot of details in it and various tricks on how you can actually perform optimization. So a suitable choice of this function q can get you very far. Question? Yeah.
Are there any results about the tightness of the bound, like how close is the lower bound?
Okay.
On the functional form or something else?
Well, so there are no general bounds in the sense that, well, here's a given function class and here's how bad it can get. However, for instance, one thing that you can easily check is you can just, ask how large is the discrepancy between the class of functions that I can model with q and the class of general functions p of y given x that I could have in my statistical model. And then you need to work out the algebra, and you could probably get some guarantees there. It's a good question. Usually people don't bother, and they just say, look, it works. One of the reasons why that's the attitude is because you have the much bigger problem of simply not getting a global minimum anyway. So since you're not getting a global minimum, asking about how good your variational approximation is sort of a secondary effect, at least in some cases. But I agree it should be studied a bit more. But in the case of clustering that we're going to look at right now, there is no limitation because we're not using really variational EM, but we just use the full function class. Because the P of y given x is such a simple function that we can explicitly write it out. That's the main reason. So what you therefore get is this very simple iterative procedure. You compute Q of y, and then you maximize. Computing this Q of y actually turns out, if you go through the algebra, to computing the tangent on the function that I showed you before. Seeing that connection requires a bit more algebra. I wanted to show you both things intuitively. Putting them together is something that you may want to do as a bit of homework. Okay. Now, how does it look like in practice? Okay, so our factorizing distribution for clustering is going to be a very simple one. We just say Q of all the y's is just the product over all the i's, Qi of y. So basically, I'm just modeling for each single data instance, what the distribution over the clusters is. The E step then is, well, okay, so what do we get? So Q of y is proportional to P of x given y, mu and theta, mu and sigma, and P of yi given theta. So that's my current model. I need to renormalize that. That basically just tells me how well does a particular cluster fit a particular variable. And then, well, just plugging that back in, I get these weights, right? So that's just the unnormalized expression here. That's the normal distribution. These are the unnormalized probabilities. And then that's what you get after you normalize. So this is very simple. You can just take that equation directly, type it into Python or whatever, and you'll get something useful. Then the log likelihood. Well, now we have the log likelihood, P of x and y given theta, mu, and sigma. It's just, log of P of xi given y, mu, and sigma, plus the corresponding term log of P of yi given theta. And then, now all we get is just we have like what we would have standard for estimating a Gaussian, except that an instance now spreads its weight over possibly several clusters. So I can have a situation where maybe I'm not sure which of those three clusters it is, and maybe each of those clusters has like weight gets 1/3 contribution. Then I'm just adding 1/3 of its mean to each of the cluster centers. So that's what I get. So mu of y is 1 over ny, summing I equals 1 to n, Qi of y xi, correspondingly here. Once I do this, I can likewise also get, cluster probabilities, so basically theta star. And in that case, all I have is just, those fractional probability weights divided by, the total count. So this is very simple. It's really just estimating means and variances, just that now data points can have fractional weights. So I get those fractional weights, I update my means and variances, and then, again, I compute my Q, and I iterate between those two steps a couple of dozen times. That's EM clustering. It actually works fairly well. Here's an example, some data, and OK, so you get the cluster centers, if you get lucky. OK, so here are a few problems, right? The estimates might actually diverge, right? So you might get infinite variance, zero probabilities, tiny clusters, all sorts of mess. So what's going wrong? Well, what's going wrong is that we didn't actually use our prior on what the means and variances and so on ought to be. So we just used the priors. And as I said before, I'm using conjugates because they make the algebra particularly nice. And so that means a Dirichlet for the cluster probabilities, a Gauss-Wishart for the normal distribution. And that's what we get. So each cluster count now is the probabilistic weighted count plus then some baseline counts here. For instance, I make n naught 1 or 2. I'm assuming basically, there is not going to be a single cluster that has fewer than 2 instances in it. Furthermore, I'm going to assume that maybe, the means and variances are 0 and identity respectively. So I just downweight things. And here's for the covariances. So for the cluster probabilities, for instance, I get this. Then as a result, I just get the counts here plus, n plus. And there's actually a small typo. I would actually need to write here ny plus n naught. Okay. So the algebra hasn't changed. I'm just adding fake data to it. I'm just adding a little amount of fake data that is drawn from a zero mean unit variance normal distribution, and I'm assuming maybe there are 2 data points of that form in each of the clusters. That immediately prevents the variances from going to 0, which also means that the cluster probabilities will never be 0, and so things actually work out. Okay. So as stated, this is the variational approximation. What we had is that log p of x parameterized by theta is just this expected log likelihood and then an entropy term. So just to repeat, we find q within some subset. So that's the variational method. Rather than taking all of them to tighten that inequality, and then we optimize over the parameters and we iterate. And at each step, our guarantees get better because, well, this was a lower bound. So if we make it tighter, things can only get more accurate. If I then maximize that lower bound, I'm also increasing things. So at each step, I'm moving up. It's like a ratchet. And that way, you ought to actually do something useful. And there are many cases when variational methods are really the way to go in graphical models. However, one thing to think about is that in many cases, they amount to using dense variables or dense linear algebra for an optimization or estimation problem. In some cases, sparse variables may actually be computationally more efficient, and that will get us much closer to sampling. Okay. Any questions so far? Okay. Everything clear? Or everybody's really tired? Okay, I hope it's clear, not tired. Okay, now let's, beyond simple mixture models where you can do interesting things, but I'm going to talk about sampling now. So here's an example where maximization isn't necessarily the best thing you can do. Suppose that's my posterior. Then, well, going for the mode isn't a particularly brilliant idea because the mean's actually here. Right? Quite often that doesn't happen because you get concentration of measure and all sorts of other interesting effects, but in general, mode and mean are not the same thing. And in some cases, you actually care about means. So here's what you can do. You want to get a sample from the actual distribution, right? So we could just sample from that posterior distribution rather than maximize it. And if we could do that, everything would be nice, right? However, drawing directly from some complicated distribution of random variables is in general impossible, so we have to approximate. And what I'm going to show you is one hack of how I can go about it. And this is called Gibbs sampling. There's a special case of a much more general family of algorithms, namely Markov chain Monte Carlo sampling. And I'll just show you the really simple one. And that'll actually get you pretty far already. So here's the idea. Suppose that I have a distribution of random variables x and x prime, And drawing from x and x prime jointly is really expensive. So let me give you an example. Suppose I have some two-dimensional distribution, and it has some interesting form, whatever. I guess I'm probably going to draw something that looks almost like an amoeba. But let's even make things simpler. It's discretized. And I have, n bins here, and I have n bins there. Then drawing from that, at least if I do it naively, will cost me order n squared operations. Because I need to sum over all those little bins, and then I can sort and draw from them. So order of n squared is sort of what I would expect.
What are you drawing here?
I want to draw from that distribution. That's the probability density function. So I would probably get a lot of points from here and there. But occasionally I might get some points out here too. So in other words, drawing from that two-dimensional object may be fairly intractable. However, it's quite possible that if I slice this, that is, if I just were to cut it here, I get something that's fairly easy to deal with, right? At least now I only need, if for instance I knew the value of this variable here, let's just call this x and x prime, then maybe p of x given x prime might actually be easy to obtain. Okay, so maybe we end up here. Then I go and slice it again. So now I fix x prime, and I cut a slice along here. And now I draw from p of x prime given x. And maybe I end up here. Then I go and slice again. Now, keep in mind, each of those steps is order n. So this is order n. It's order n. And of course, this is also order n. So now I can actually do things a lot more efficiently. And yes, it's sort of like coordinate descent, but you're actually drawing from that distribution. And what you would hope for is that you're drawing mainly from the modes rather than doing anything else. This is called Gibbs sampling. So if I have more than two variables, let's say I have variables x1, x2, x3, then I would draw x1 drawn from p of x1 given x2, x3. Then I would draw x2 from p of x2 given x1 and x3. And then I draw maybe x3 drawn from p of x3 given x1 and x2. And then I iterate again. And I do this for some time. And some time is a function of how much computer I have, how patient I am, how much I care about quality, how nice the problem is, how many times somebody else who's written another paper on that subject has drawn the samples from. And then, if I'm satisfied, I take this as a sample. I might want to draw more than a single sample from it. That really depends on exactly the problem I'm trying to solve. And this will give me a sample from the posterior. So let's just look at that for the case of, just drawing from, the space of predictions of, what the doctor does, and then, whether it's actually a boy or girl. So we initialize somehow, and then, we just alternatingly draw and keep on doing that. That would be a simple Gibbs sampler from that 2x2 table. Obviously, I wouldn't be as insane as doing that in practice. This is a more realistic situation. And in general, you might have billions of variables where you draw from. Yes?
This might be a naive question, but have you tried abstracting Gibbs sampler or a modification of
Okay. Perfect question. Thanks a lot. So there are some distributions for which Gibbs sampling may work fairly well in MapReduce. As a matter of fact, if I do clustering, that actually works quite nicely, at least in the naive setting. Okay. So let me show you what happens. Oh, yeah, here we actually have that, right? Okay. So, well, what you would be doing is you would, for instance, in a map phase, draw all the yi's given xi's and theta and phi. So map draws yi from P of, yi given xi, phi, and theta. And since this decomposes nicely and it decomposes over all the instances, I can actually do the sampling step. Then I run reduce, which does the following thing. It aggregates sufficient statistics, and it draws, and then I have some intermediate step. Let's call it master. And this draws basically phi and theta from some P of phi and theta given the rest. So in other words, I do a map stage, I do a reduce stage, and then I update my global parameters. And if, for instance, you look at Mahout for clustering, the code will pretty much look like that.
It's also very similar to the Gaussian solution.
Yes. So big warning, do not use Mahout Dirichlet process clustering. Their code is buggy. They normalize every Gaussian in 2 dimensions, which works beautifully for 2-dimensional test cases. And if you have higher dimensions, the normalization is wrong. Now, that's not just a small pesky issue. It actually means that the cluster probabilities are wrong, because if I have different variances, things are wrong. So be careful when you use it. You need to fix this. Any more questions?
So basically, you mean that all the exponential family Gibbs sampling can be accepted in the...
You could, so not just exponential family Gibbs sampling. It really depends very much on the model. You could do LDA in the same setting. There are a lot of cases. Now, the question is, why would you not do that, right? So here's one pretty strong reason why this is a bad idea, or why it's actually really not the best thing you can do. This algorithm doesn't mix very fast. Basically, only after I've updated all the cluster assignments will I update the model parameters, and then I will update the cluster assignments. So you may need to run maybe a couple of hundred MapReduce iterations. Now, if you know that each MapReduce iteration requires you to basically allocate the machines, move the data around and all that, and then it requires a lot of copying to disk and loading from disk, it basically kills performance. You can actually check that in some cases, the algorithm will get slower the more machines you throw at it. We had a proof by example with a rather unfortunate intern who did his internship in Yahoo just around the time I arrived, and at some point he sent me an email and said, I've parallelized LDA, and then I looked at it, and his code got slower the more machines he had. And he shall not be named. That's the first problem, that actually communication isn't very good. The second really bad thing is that you have this step here. So basically, after you've aggregated everything, all the machines go idle. Maybe they do something else in the cluster, but in that case, you'll have trouble getting them back again, during which time you update the global parameters. Once you've updated the global parameters, you invoke the entire machinery again, so it gets slow. Bottom line being, if you do this, you're not going to get a very efficient sampler, so don't. If you're desperate, yes, you can write a paper, or at least you used to be able to write a paper about doing stupid algorithms in MapReduce. And there are way too many papers which use a stupid algorithm and parallelize it in a way that then still gives you something that's slower than an intelligent algorithm. Okay. Let me just show you a little bit how it behaves. I mean, this is all just a made-up example. So here's some points I want to cluster. I randomly initialize, sample some cluster labels. Okay. I resample the cluster model. I resample the cluster labels. I resample the cluster model. And I keep on doing this. Yeah. Mahout-Dirichlet process clustering does something like that. One very important thing that I hope I managed to drive home with this is why I showed you a range of different inference techniques for the same model, namely clustering, is that the inference algorithm and the model are not the same thing. Corollary, EM is not clustering. Repeat after me. EM is not clustering. OK, thanks. So here's why I had you repeat it. Because I had to explain this probably about 10 times in the past 2 or 3 years in my job. OK. So this is, and some of you might at some point end up in Yahoo. So, then at least I won't have to explain it to you. So, yes, sorry. I mean, it's really blatantly obvious, but many people say, yeah, OK, and then we use the EM algorithm to get the clusters. And that's the algorithm. And yeah. OK, good. So I will conclude with a little bit of zoology, right? And that's in the context of Yahoo. And I'm doing this also for the following reason. We had this discussion in the morning about, well, how bad UCI is, right? And then the great misery was that you couldn't get the right data sets. So most data is messy. Most data will not be solved by a simple classification or regression or multi-class classification problem. It doesn't. So therefore, if you work with real data, sure, you might in the end work until you've reduced it with some modifications to one of those fairly well understood, clean problems. But a lot of the work is going to be how to reduce it to one of those well-defined problems. Okay. Now, there are lots of sources where you can get data. The internet is an amazing source for data. So let me give you some examples where you can easily get data for free. I've already mentioned Yahoo Web Scope. So let me write this up because so Yahoo Web Scope has probably about 30, 40 data sets in it. Google releases a bunch of data sets too. For instance, the Ngrams. I don't know what else they release, but you can probably get some from there. I'm not quite sure about Bing. Leon would probably know. There's Netflix. And maybe you know somebody who has the Netflix 2 dataset. They had to pull it because somebody got really upset about probably thinking they were uncovered through their search history. And then, of course, they went public to keep the information private. OK. You can still find the AOL search queries on the internet. You probably need to find it somewhere on BitTorrent. The guy who released them was fired for that, again, because somebody found themselves in it. And some of the queries are disturbing. Well, there's Flickr. And you can just download the images. There's Delicious. Well, you can just use a crawler, right? There's Demos. You can probably get some of the Facebook graph. Then there's the Twitter Firehose. And you'll have to pay for the Firehose, quite a lot. But the garden hose is free. or the sprinkler whenever it works, which it occasionally does. Then a team in Korea at KAIST actually released some of the Twitter graph. And you can find it on BitTorrent again. Then there's Spinner. They release a lot of blogs. Then there are the entire NLP datasets. And there's lots of stuff here. Tons. There are lots of microarrays. There is a lot of data that's published basically for experiments in, I think, either Science or Nature. You have to make your data available. Carsten would know more about this. But basically, I do not believe that there's a shortage of data sets. However, they may not be as easily downloadable as, wget uci.tgc. You may have to do a bit more work, and they may not be in a very standardized fashion. They may have all sorts of covariate shift issues. It's basically messy, dirty data. You may have to go and, for instance, crawl the New York Times. I know of somebody who managed to do that despite the New York Times' best efforts to prevent you from doing that. But it's all legal in the sense that, well, they were all using public interfaces, nothing that was explicitly denied. So you may have to be a bit inventive on how you get the data, but you can get it. Somebody, for instance, was trying to find out how well things sell on Groupon. So they just, crawled the pages repeatedly and checked how many people subscribe to, the feeds. So getting the data itself is going to be a non-negligible part of your machine learning problem. So if you want to get big data sets, don't expect that somebody will just drop them on your desk on a DVD. It's probably not going to happen. Okay. So this is just a very brief overview of what you could get. If you want to get some more proprietary data sets, many companies have mechanisms for dealing with that. Now, those data sets you won't just get by knocking at their door unless you're either well-known or if they trust you and you're well-known to the people you work with. So basically, if you write to some random internet company about some random data set, they'll probably tell you to go away. If you interact with some researchers, they are first for a while, they trust you, you do some work together, maybe you visit and all that, they will trust you enough that you'll actually get the data. Okay. So that's a little bit of where you can actually get data. And there are plenty of other ways. If you need labeled instances, use Mechanical Turk. It's actually cheap and noisy. If you want to get, for instance, lots of bid data, well, I haven't seen many people writing a paper about data on Craigslist, but Craigslist is a great source of data. You could just crawl it. Right? So here's a thought. Okay, now let's just conclude with that brief zoology, and then we need a break. Okay, so here's a few things. So some of the issues that you need to deal with is, you have the issue of models. You have various, statistics about statistical tools. You need efficient computation, and, well, of course, various inference methods. So let's just go through it step by step. So I could, for instance, have different priors and different, statistical formulations. That's standard tool chest. I might pick different models to describe the data, whether I have directed, undirected graphs, Markov random fields, chains, mixtures, clusters, factorization models. There's lots of stuff there. I could then decide how I will actually go and get the parameters, like exact, k-mean, skip sampling, variational, lots of ways how I can get that. And, well, in the end, well, you can, you need to do efficient computation. So, for instance, you'll probably need message passing and probably some optimization tools, possibly both, maybe some clever sampling tools to actually get a solution. All those things fit together, and the common strategy for writing a paper is you pick one each, combine it, apply it to some new data set, and you have a paper. At some point you might get bored with it, but it'll boost your paper count. More fun is if you actually do something new in one of those areas. A few places where you can actually get this. Just look at those issues. So there's a lot of stuff. So the colors basically mean this is actually data that relates to our daily business. These parts relate more to, engineering the systems themselves on which our stuff runs. You may have heard of statistical debugging. Basically, the issue is you have a massive piece of code. You want to find out where the actual bugs are. Then you can maybe put your code into a test harness, have various randomized instrumentations, and find out whether things go wrong. And if your piece of software is complex, then you might not be able to really exercise all the test cases. So think of that as an equivalent of a unit test, except that your big piece of software is complicated enough that you can't really do a proper unit test of the full system, so you might just drive it with various random inputs. And you check whether it falls over. Performance tuning. There again, you may actually want to estimate which cases are frequent, where the problems come from. System design itself, a lot of statistical analysis can help you there, for instance, with caching and so on. We've done quite a bit of that, so I'm going to skip over that. Yeah, we already had that. Chains, had the hidden Markov model, collaborative filtering, web page ranking, and I think that's pretty much the end of it. So let me just quickly show you the connection between collaborative filtering and web page ranking. Because a lot of people don't seem to see this. So this is like Netflix style. You have users, you have movies, and you get some rating, right? And people aren't using a lot of attribute features for the users in the movies. That's partially due to the terms and conditions that, stipulate that you're not allowed to use any non-free data, for instance, for the movies. Otherwise, what you could, for instance, do is you could just pull the movie attributes from IMDb, and this would be an extremely valuable additional source of data for Netflix ranking. Unfortunately, it's not freely available. Web page ranking, usually what you do is you might have obvious attributes of a document, of a query, and then you do massive feature engineering to get this. But actually, what we could do is based on user response, how much users actually like it, we estimate the latent attributes of the documents and queries, and we combine both. And that gives you better web page ranking, and by now, a lot of the technology is moving in that direction. So you may have heard of this, bit of a storm in a teacup about Google finding out that Microsoft Bing search was, quote, copying their, spelling correction or other things. And basically all that happened is that, basically they fed the Bing toolbar with fake query and then click responses. And, basically using user data and user behavior to feed your ranking model is fair game. And the Bing model learned this. And then there came this big outcry saying, oh my God, Bing is copying Google search results. Well, you can interpret it this way. You can also view it simply as, Bing was making good use of user data. And yeah, I have no stake in it insofar I can easily argue that. Of course, that's not the end of the story. This is what you want. Basically, you have a user, and you have some obvious demographic features. You might have some latent ones, and you use them to modify that ranking. This gives you interesting systems questions because now, so before that, for instance, you could have cached all the search results for a given query, at least for a couple of seconds. Now, since I don't know that, for instance, Vishy is going to show up on the web page, and he particularly likes maybe Indian things in his search results, so then, if I have to generate all the search results just right at the moment when he shows up, the results will be too slow. Because I want to have maybe 100, 200 milliseconds result time. So how do you build a system that gives personalized results, yet retrieves them quickly? In some cases, then the question is, how do I create the impression of providing results quickly, even though it isn't really the case? So particularly nice case where, at least I believe this is how it was implemented, on Bing search at some point, Twitter results started showing up. And they scrolled through very nicely. If you looked at it initially, you would think, yeah, they are very nicely real-time search results. It actually turned out that they were just all downloaded at once and then scrolling through slowly. And to the unsavvy user, this is just as good. There's no real difference. But it just made a big difference, I would imagine, in the back end. OK. That's pretty much what I had here. I want to conclude with data integration. So here's what we had. We had users, documents, queries, and then we get the web page ranking. Now, suppose I add display advertising to it. So I get the clicks. Again, I have documents. I have ads. But it just also so happens that the user, of course, matters for that, if I know something about the user. So whatever the user queries now tells me something about whether he's going to click here, right? I might also use that to show him more relevant news and vice versa. Tells me something about some other documents. And then maybe I have some answers that I show the user, also with different ads here. So basically, I have an entire network. And what I'm going to conclude with in the break is now topic models. And I'll just show you the graph. And then that's it until the break. So basically, the idea is you have personalized clustering. So it's just like you cluster words, but you assume that the distribution over clusters per document is different. OK. And I'm not going to show you any more than that now. You can ponder over the graphical model in the break. How much break do we have, Vishy? 15 minutes. OK. So we start then at 3:25. OK. Thanks.